Hello everyone, and thanks for joining me at Cyberllama Talks again. I hope now you know very well how Process Emulator works and how it was used both for fighting polymorphic malware and unpacking polymorphic layers, and also for behavior analysis and a code structure and memory analysis of the samples. Today, a little bonus video. I actually will show you how the same concept which we used for process emulation was also used for rootkit emulation and detection of kernel mod rootkits. The same as in a regular CPU emulator and also the process emulator, we start with the vCPU, stack, and virtual memory, and specifically virtual memory manager, who is going to manage how source virtual addresses map to a target emulated virtual address. However, there is a little special detail. Since we're emulating rootkits, and specifically kernel rootkits, the virtual memory we're going to be emulating is actually kernel memory, meaning it's an upper bound of the addresses which are allocated for Windows in kernel. And the same way as a regular malware was mapped into the memory by a process emulator to emulate one process virtual space, the same way rootkit can be mapped to the kernel memory. You see, the kernel memory in Windows is shared by all processes, so it's just only one copy of the kernel memory. Meaning, in principle, when we're talking about emulation, emulating a kernel driver is very, very similar to emulating just one process, because it's just one copy of the memory. In our case, it's just a kernel memory instead of userland memory. However, of course, there is a special things we need to emulate if we're talking about the driver. There is no PEB or TEB inside the driver, because PEB and TEB are both user mode structures. However, when we talk about the drivers, there are of course also a kernel structures which describe processes, threads, and other objects. So if emulator wanted to be a kernel mode emulator or driver emulator, it would need to also support structures such as eProcess, eThread, and those not just one structure per driver, of course. Those structures, they described all the processes and threads existing in the system. Meaning, if a driver emulator would want to really emulate the kernel mode properly, it needs to emulate those lists with the multiple processes, and that's a bidirectional list, and the same with the threads. Right? And of course there's more than two, there are many of them, and they describe all the processes and threads existing in the system. And of course this eProcess and eThread is multi-layered structures, meaning multi-level structures. So the eProcess consists of other structures and other structures and other structures. The same way PEB and TEB addressed using segment registers such as FS and GS, the same way kernel structures, eProcess and eThread actually accessed through the same segment register. That the segment register just has a pointer to a structure which has a pointer to those two lists and some other substructures. So those are main structures which needs to be emulated to support list of processes and threads. Of course, we also need to emulate SSDT, interrupt descriptor table. So we have a system service descriptor table and interrupt descriptor table, which a rootkit can try to access. We also need to emulate NT, OS, kernel.exe, and a bunch of other standard drivers we might want to have, like a TCP/IP.sys or Win32k.sys, and so on. So there might be multiple drivers depending on the type of rootkits. And maybe a bunch of other structures, again, depending on what rootkit is doing. There might be a few extra structures in the kernel the rootkit emulator or driver emulator want to emulate. However, all this idea is kind of the same as the process emulator, right? It is a CPU emulator which aware about extra context, and if in case of process emulator, the extra context was a context about the process, now the extra context is actually about the Windows kernel. But the idea is the same, it's just the address which gets translated to some meaningful target virtual address with the content of the structure. And emulation loop is the same. Remember that loop when we fetch, disassemble, lookup, emulate, and so on? It's the same thing here. Of course, it now needs to also support import table of the driver, right? So it supports kernel level APIs, to be more precise, right? Imports and APIs. But it actually happens very similar way. If the driver has a call, or a driver, for example, searches inside these modules and tries to find an exported function which it wants to call, it's the same idea. That when emulator handles the call instruction and it sees that virtual address goes beyond the virtual addresses of the rootkit itself, it needs to analyze that virtual address and understand what function is actually being called outside of the rootkit itself. There are a few more things the rootkit emulator or driver emulator would need to support. As you may remember from our rootkit video, the rootkits are not the same as regular executables. They don't just execute from an entry point to the end. They do have entry point, the driver load entry, where the driver can, for example, unpack itself if it's a packed rootkit or perform certain other computations. But what also can happen inside the driver entry is the driver will register IRP callbacks. IRP stands for I/O request packets. So any I/Os which happens in Windows, if it's a file I/O or network I/O or any other ones, would go through the stack of the drivers who register the IRP callbacks. And usually you would see them something like IRP major create. It means if that event happens in the system, the driver callback would be called. And a lot of rootkit activity might actually happen inside those callbacks. For example, if rootkit wants to hide a file or do something else, or for example, rootkit implements certain communication with the user land using IRP major device I/O control, then the user land can call device I/O control and pass certain parameters in a rootkit, and then rootkit would receive that callback from device I/O control by that IRP callback. That IRP callback is going to be, in this case, IRP callback is going to be called and receive the data passed by user mode process. So if the emulator wants to emulate such a callbacks, it means the emulator also needs to support parameters, because those callbacks, they receive a parameters inside. So it means emulator doesn't just emulate the structures and emulation loop, but it also needs to be able to call different registered IRP callbacks with the parameters those callbacks expect. The good thing is, since those IRP receive the call from the Windows, right? They called one after another when they on the driver stack. Then a lot of the parameters are the same. For example, IRP packet itself is going to be the same. Of course, when the rootkit's callback will start to parse the parameters and try to read some buffers from a user mod, the passed from user mod, the rootkit emulator might not know, and most likely would not know what structure it needs to pass. But at least just by calling them and emulating them with some standard buffers passed around, the rootkit emulator can pass far enough to register certain API calls, and also making sure that all the code unpacked, so the rootkit emulator can perform, again, memory analysis and call graph analysis on all the APIs available inside the rootkit. So that's how the same concept we used inside process emulator was applied for rootkit emulation or kernel driver emulation in some of the products as well. Besides unpacking packed kernel drivers, the rootkit emulator would also look at what kind of memory structures and what kind of register the driver modifies. For example, it was very typical for rootkits back in the day to modify a control register, which called CR0, and specifically modify WP flag inside them, which stands for write protect. And so if this flag is reset, what happens is the driver could change the read-only memory inside kernel. And of course, all the system structures are read-only, so when this register is modified, the next thing the rootkit can do is to change SSDT table. While emulating the code, first the emulator could detect, since emulator emulating instruction by instruction, it can detect that CR0 was modified and WP flag was reset, and then it can actually see that the rootkit got the address of SSDT and modifying a memory inside a table. That alone already give a pretty much super high confidence that that's a rootkit and it can be detected. So while it's not always necessary, it was not always necessary to actually emulate rootkits, because most of them were not packed, and sometimes it would be just simple disassembling and reconstruction of the control flow graph would be enough to just see that instruction of CR0 and see that it's trying to access SSDT table. Some of the more sophisticated rootkits would actually packed. And for those type of rootkits, the Rootkit Emulator would be a very essential tool to detect them, because without that, again, the signature would not be sufficient, and behavioral analysis of the driver cannot be really performed on a live system. So the Rootkit Emulator would be the best way to perform behavioral analysis of the rootkit. I hope you enjoyed this little bonus video about rootkit emulators, and now you know how the same concept which we used for the process emulation was also used, of course not by all the vendors, but by some vendors, to perform a rootkit emulation, and that allowed to detect rootkits, even more complicated rootkits, which were packed and which maybe obfuscate strings or obfuscate the intent, for example, dynamically resolving APIs. So the rootkit emulator would allow antivirus to emulate far enough to reconstruct either strings or reconstruct the call graph or control flow graph, and actually analyze the rootkit and detect it, both based on the memory analysis of unpacked memory during the emulation, as well as a behavioral analysis based on all the APIs and registry modifications such as CR0, which rootkit perform. Hope you enjoyed that lecture. Please don't forget to subscribe, share, and I hope to see you next time.